Okay, so let's talk about inverse functions. Before we get there, we need to talk about a one-to-one function. Now, here's the deal. A one-to-one function, first and foremost, is a function. And remember the definition of a function. Every input has one output. That's a function. Now, for it to be a one-to-one function, the reverse has to be true. So, one-to-one is not only a function. The other half of the definition is every output has only one input. So let me give us an example because it'll make things a little clearer. Let me look at y equals x to the second power. Now, if I plug a number in for x, let's say 2, I get a 4, correct? So this is definitely a function, which means the y will change, and this will be notated as a function. Now, for it to be a one-to-one function, so this part is true. For it to be a one-to-one function, every output has only one input. Okay? And I should say every output's value has only one input. For example, if I plug -2 in to this function, I still get a 4, don't I? This is a function because every input has one output. But in this particular case, this output is the same, and it comes from 2 different inputs. That cannot happen for a one-to-one function. That cannot happen for a one-to-one function. Every input value has only one input. Every output's value comes from a single input. These 2 outputs are the exact same number, and they come from 2 different inputs. This is not a one-to-one function. Okay? It's not. With me? All right. Now, some of you may be asking, well, why is it so important to identify one-to-one functions? Here's the deal. One-to-one functions, oops, sorry about that. A one-to-one function has an inverse. And that's important. If a function is not one-to-one, it has no inverse. That's important. Got it? Okay, so let's take a look at some examples here. They're going to ask us if these examples are one-to-one functions. So let's look. They say if it is a one-to-one function, they would like you to find the inverse. So let's stop there a second. First, I need to determine if it's one-to-one. Remember, not only does each input have exactly one output, which we're seeing in this case, every input has exactly one output. But remember, every value of the output comes from a single input. Do you see these 2 outputs? They're exactly the same, aren't they? And they come from 2 different inputs. Is this a one-to-one function? No, this one's not one-to-one. And since it's not a one-to-one function, there is no inverse. Not one-to-one, no inverse. You with me? Okay, let's look at another example. I'm looking at every input, and I'm seeing that every input has exactly one output. Now, let's look at the outputs. Are any of the outputs duplicates? No, they're not. So would this be considered a one-to-one function? Yes, this one is a one-to-one function. Yes, one-to-one. Which means it has an inverse. Now we have to figure out the inverse. Now here's the cool thing about a one-to-one function. Yes, it has an inverse. And the inverse, to find it, is very simple. The input and the output switch. For one-to-one functions, your input, when you're trying to find their inverses, the input and the output switch. So my input was the states A, B, C, D, and F, which means for the inverse function, the states will now be the output. So let's look at letter A. My states are the output. That's good. Letter B. Wait, they still have the states as the input. It can't be this one. And letter C we already know is out because we said it was a one-to-one function. So my states on the original were the input. Since this is a one-to-one function, it has an inverse, and the inverse is going to now have the states as the output, which means the output now becomes your input. So for state A, its input is 1. For state B, its input is 49. For state C, the input is 14. For state D, its input is 27. For state E, its input is 36. And last but not least, for state F, its input is 7. This is the beauty of one-to-one functions. They have an inverse, and the domain and the range switch on us, which is perfect. Now let's take a look at this. They're giving us a set of data points, and they want to know if these points are representing a one-to-one function. So for us visual people, sometimes it's a little bit easier to draw these mappings as we have dealt with in the past. And since they're points, we have x's and y's, right? Okay, when you list your x's, if there are duplicate x's, don't write them down. And the same with the y's. If there are duplicate y's, we do not write them down. Okay, so according to the first point, -5 gets mapped to -5. 7 gets mapped to 7. 3 gets mapped to 8. And 8 gets mapped to 3. So this is definitely a function, and it is clearly a one-to-one function. I don't see any duplicate y values, so I don't have to worry about two different inputs to give me the same output. Now, since it is one-to-one, this notation means inverse. This little -1 means this is an inverse function. And remember what we said, the inputs and the outputs will switch, which means I've got to now switch my x's and y's. So I have a little bit more room down here. Letter A is the answer. So the inverse function, so my input now is -5, and my output is -5, so that really didn't do anything for us, right? The input is now 7, and the output is still 7 over here. The input is 8, and the output is 3. The input is now 3 here, and the output is 8. This would be my inverse function. Cool? Okay, let's take a look at another one. They, again, would like you to determine if this is representing a one-to-one function. So once again, I think it's a good idea to draw ourselves a mapping. The x's are the inputs, the y's are the outputs. X's, I do not see any duplicate numbers. The y's, I don't see any duplicate numbers again. And this 17 gets mapped to 18. 5 goes to 2. 2 goes to 5. 9 goes to 9. So yes, it's one-to-one. Yes, one-to-one, which means it has an inverse. And the inverse notation is the function notation with a little -1 in what looks like an exponent position. Okay, so that will be letter A. And they want us to literally write the inverse. Remember, since it's one-to-one, your x and your y are going to switch places. So, again, I'm going to write my answer down here because I have a little bit more room. So, remember the brace means the set. So, the set of, 18 is now the input. 18, 17. On the next one, the 2 is now the input. 2, 5. On the next one, the 5 is the input, 5, comma 2, and the 9 is now the input, 9, comma 9. Cool? Okay, loving it. Let's look at a graph. I need to know if this graph is going to represent a one-to-one function. Now here's the deal. It's definitely a function because every x goes to exactly one y value. But I have to make sure that every y value has a single x. Here's a y, and gratefully it comes from only a single x. Here is another y, and when I push it to the line, it only comes from a single x. This one is definitely a one-to-one function. And some of you are like, okay, I am not quite certain this is one-to-one. Let's look at this example. This is definitely a function because every x goes to exactly one y value. Now, the reverse has to be true. Here's a y value. Where's the x that gives you this y? According to the graph, this x gives me this y, and this x gives me the same exact y. That cannot happen. This is two different x values that give me the exact same y value. This cannot happen. This is not a one-to-one function. Where is this last one? Here was a y value, and according to this graph, this was the only x that gave it to me. Here was a y, and that was the only x that gave it to me. Whereas on this one, this y value came from this x and this x. Definitely not one-to-one. Look at this one. What do you think? Do you think this is one-to-one? I'll give you a moment or two. Yeah. I am seeing this. I can pick any y value. Let's pick this y value. I see this y value comes from this x. It comes from this x. Uh-oh, wait. I see it over here too. It comes from this x and this x. Oh, it comes from way too many x's. Is that one-to-one? No, definitely not a one-to-one function. You with me? Okay. I think we've got one more. Okay, let's take a look. They're telling me that this is a one-to-one function because they say graph the inverse. And since they say graph the inverse, I know this is already a one-to-one function. Now, remember what we mentioned. The x's and the y's will switch places. So if I pick a couple of points, this point, and let me erase so I've got a little more clarity. This point right here looks like the point 10, comma 2. And this point right here looks like the point 2, 4, 5, comma 0. If they want the inverse, remember, things switch. This is the original function. The inverse will have the point 2, comma 10. So the point would be 2, comma 10. And this other point would be 0, comma 5. So if we graphed these, 0, 5 would be here, wouldn't it? And 2, 10 would be here, wouldn't it? My graph would actually look like this. Remember, the x's and the y's are going to switch on the inverse. So it's important to know what points you have so you can switch them around to find the inverse. And when I did that and plotted, is it letter A? Nope, because it doesn't look like this graph. So letter A is gone. Does it look like B? Yeah, it sure does look like B. Does it look like C? Nope, because C, our other half is not down here. And D? Nope, other half is not on that side, so that's not it. Letter B would be the graph of the inverse. Does that make sense? Okay, so hang in there. I'll be right back with some more examples. Okay, so let's talk about how to find the inverse of a function. There are 4 short, simple steps to find the inverse of a function. I've written them down here, and we're going to work out an example at the same time. So here's the first step. It says replace f of x with y. So instead of f of x, we're replacing it with, we're replacing it with y. Now, some of you may be going, why are we doing that? You know what? It's just easier to look at. That's it. It's purely for aesthetics. Don't get too bogged down in this first step, okay? The next step says switch x and y. So x is going to get switched with y. And again, some of you may be going, why do we switch x and y? Remember what we said about inverses? Wait, what used to be the input is now the output, and what used to be the output is now the input. They switch around, which is the beauty of inverses. They switch on us. The input now becomes the output. The output is now the input. It switches on us, so this is actually a really good thing. The third step says to solve for y, so I need to get y by itself, which means I'll add the 3 over. And last but not least, I'll divide by 3. Good? Okay, and then the very last step says, replace y with f to the negative 1 of x. This is the inverse notation. You see that negative 1, that means inverse, which means when I say f to the negative 1, I mean f inverse. So f inverse of x is equal to x plus 3 all divided by 3. Cool? You with me? Okay, hang in there. I'm going to show you how to check this problem to make sure that this is truly the inverse of the original. Okay, so let's check and make sure that this inverse we found is truly the inverse of 3x minus 3. And you're like, well, how do you check it? Here's the thing. Checking is a two-step process. It's 2 parts. I have to make sure both parts work. So, one of the parts I need to check is I need to check f composition f inverse of x. And the other part I need to check is f inverse composition of f of x. And both of these need to give me the same answer. Both of these need to give me just x. Everything else should cancel away, and the only thing that remains is just x. So I have to check both of these to make sure that this works. Because believe it or not, on a rare occasion it doesn't. And that doesn't mean we did something wrong, though I would check to see if I did anything wrong. It just means that it just didn't work. So here we go. Let's check the first one. Let's do f composition f inverse of x. Remember, that means take f and you're going to substitute into it the inverse function. So I'm going to take f and I'm going to plug into it the inverse function. I'm going to take f, which starts with 3. I'm going to substitute into it the inverse function. And f says minus 3 after it. Okay, so do you see what's going to happen here? Do you notice these 2 3's are going to cancel? And we're left with x plus 3 in the parenthesis, but then minus 3 on the outside, which, yeah, gives me just x, which is exactly what I'm supposed to get. Okay, this part worked. Yay! But I got to check the other one. I got to check f inverse composition f of x. So remember, that means the inverse function is going to have f plugged into it. The inverse function, you're going to plug into it the original function of 3x minus 3. So the inverse function, which starts off with x, which means I am going to write 3x minus 3. And then it says add 3 to it. And then it says divide by 3. Well, look what happens in the numerator. This minus 3 and plus 3 will cancel, which leaves me 3x over 3, which leaves me x. Oops, not a negative sign, just x. Okay, so on both cases, I got x. Are these two inverses of each other? Absolutely. We did everything correct. Big old check. Okay, hang in there. Got some more for us to work. Okay, still finding the inverse. Let's look at number 2. So remember your steps. First step was to do what? Yes, replace f of x with y. So, what did our next step say to do? Good. Switch the x and the y. What did the next step say to do? Good. The next step said to literally solve for y. So in this particular case, the first thing I need to get rid of is that cubed root, isn't it? And what cancels a cubed root? Good. A cubed power, or a third power, cancels a third root. So I am going to have to take both sides and raise them to the power of 3, which means I'll get x to the third equals y minus 4. With me? And then add the 4 to both sides to get the y by itself. Cool? And then the very last step said replace the y with the inverse notation. Good? Are you with me? Okay. You can check to make sure that this is the inverse of the original, like we did just a few minutes ago. But I'm going to make certain, or I'm going to trust myself and say, yep, I did everything correctly. Okay, let's look at problem 3. Still finding the inverse. So, first step, good. Replace that f of x with a y. Excellent. What's the next step? Good. You're going to switch the x and the y. And now what? Good. Solve for y, which means I need to get this denominator gone. So I'm going to multiply both sides by this denominator. So these cancel, don't they? Which leaves me 4y plus 1 times that x. Agreed? Okay, so I'm trying to solve for y. I don't like this multiplication problem here, so I think I'm just going to distribute. Well, that's a lot nicer looking. And I want to solve for y. I need to get y by itself. So, yep, move that x over. And then last but not least, to get y by itself, good. Get rid of this 4x by doing what? Excellent. Dividing. So you're going to have y equals 4 minus x over 4x. Remember, we divided in this case both sides by 4x. So those of you who need to write that little step, make sure you write it for yourselves. Cool? Okay. Last but not least, get rid of the y, put the inverse notation in, and here is the inverse of the original problem. Cool? Okay. You have fun with this stuff, and I'll catch you on the flip side.